This is our third and final video on periodic trends and concludes the material for Chapter 8. So far we've talked about atomic and ionic radius, ionization energy, and electron affinity. We're going to finish up by talking about the metallic character of elements and their magnetic properties. So when we say metallic character, we mean how much like a metal does this behave. They're malleable and ductile, so they're bendable and shapeable. They're generally shiny solids. There's only one metal that is a liquid at room temperature, and that is mercury. They are good conductors of heat and electricity, and the reason they are good conductors of electricity is because they readily lose electrons in reactions. And conductivity relies on a flow of electrons. So you can imagine that if an atom held onto electrons really tightly, it wouldn't be a very good conductor because the electron couldn't then leave the atom. So the ability of these electrons to flow from atom to atom is what makes them a good conductor. And so keep in mind this losing electrons in reactions, because that is really important for how we determine metallic character. So as we go across a period, the metallic character tends to decrease. But then as we go down a group, the metallic character increases. So this is a little different than what we saw before. So let's take a look at this third row here. So with sodium, we're at 1s2, 2s2, 2p6, 3s1. And then with our magnesium, it's the same but 3s2. Aluminum, we then have a 3p1 and a 3p2. So the ionization energy is going to decrease as you go to the left, making it would be easier to remove electrons, because if you remove the 1 from this one, it's really easy to remove that 1. Really pretty easy to remove those 2. And then we're into the p orbitals, but we can lose 1 here and lose 2 here. So if we think about just removing 1 electron, you take this one away, it's at a stable configuration. Perfect. Done. Easiest. You lose 1 here, it's getting closer to its stable configuration. Still got 1 more to go. For aluminum, you're going down to 3s2, but you're losing that 3p1, so that's a little more favorable than silicon, because then you're going to have a 3p1 configuration. Okay? So as we're going left in a period, the ionization energy decreases. And so as we are losing electrons, that's metallic behavior. So if the IE decreases, the ionization energy decreases, then that means that, that the metallic character is increasing. So this is the most metal-like, and this is the least metal-like, which isn't all that surprising because these aren't even metals. All right, let's look as we go down a group. So phosphorus, arsenic, I can't remember what this one is, and then bismuth. Strontium. Nope, that's not it. I don't remember. Sorry. So with our phosphorus, 3p3, 4p3, 5p3, 6p3. As we get bigger and bigger and bigger, remember it's easier to remove those electrons. And they're all just being removed from a 3p3 or 4p3, 5p3, 6p3, so the orbital is kind of the same, but it's just bigger. And as it gets bigger, it's easier to remove an electron. So as the atomic radius increases, it becomes easier to remove electrons, and losing electrons is metallic behavior. That means that metallic character increases as you move down a group. So metallic character increases down and to the left. Just be careful because these over here aren't actually metals, so talking about them as metallic character is not really important. And the key for this, again, is how easy is it to remove an electron. So metallic character and ionization energy are closely related. Okay, So why do we even care about these electron configurations so much? And the reason is that it really helps us explain that odd behavior that we see. And so I've showed you this figure before. Some transition metals have irregular electron configurations. And remember, these are what we predicted, but this is what we found experimentally. And again, we're going to go with the experimental. You don't have to know this by looking at it. It would have to be determined experimentally. But we want to be able to explain what we see when we see experimentally determined results. So the ions of transition elements, let's take a look at vanadium for fun. So here's our vanadium. We have argon as our core, and then we have a 4s2 3d3. And then for V2 plus, it's 4s0 3d3. Like, wait, hold on. When we filled this, we filled 4s before we filled 3d, right? That's why there's 2 here and only 3 here, not 10 here and none over here, right? So why are we removing them in a different order? Well, for the transition metal cations, we have to remove, the electrons are removed in something that is not reverse filling order, because remember, those orbitals, the d and the s orbital, overlap so much. And it's more stable for the electron to just have an empty s subshell than it would be to have a partially empty d subshell. Okay. So how do we know this? I told you that these were determined experimentally. So I'm going to show you the data that how we determine this. And it has to do with the spin. So when something is paramagnetic, it is an atom that contains unpaired electrons. It is attracted to an external magnetic field. It has a net orbital spin of +0.5. So you can see that these are all lined up, okay? They are attracted to the field. When all the electrons are paired, they get repelled by the magnetic field, and so there's no attraction. These are all momentum. These are, okay? So there's no attraction here. So the net orbital spin is 0. So here's our magnetic field. And when these are attracted to the magnetic field, and these are not. Okay, so these are all lined up. These are repelled. So I'm going to show you this little video that kind of lets you observe the magnetic activity of some of these elements.
You might not think of water as being magnetic, but it is, and so are graphite, aluminum, and glass. This is a new and different category of magnetism called either para or diamagnetism, and it's different from the magnetism that you're used to. You're probably already familiar with ferromagnetism. Ferro means iron. An unmagnetized piece of iron, or nickel or cobalt, becomes a magnet in the presence of a magnetic field. The effect is strong and lasts even after the magnet is removed. Paramagnetism is a similar effect, except that it's much weaker and temporary. Aluminum is a good example of a paramagnet. And so is oxygen, which is attracted to magnets. Here, I have a few milliliters of liquid oxygen, which sticks to the magnet. I'll explain why later. Gadolinium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet.
Okay, so we're not talking about a magnet like something that'll stick to your fridge, like a piece of aluminum is not going to do that. But what's happening is when there's a magnetic field, these electrons that are unpaired kind of line up, and then they're attracted. So this is the very short temporary attraction that you see. Whereas if it's diamagnetic, you don't see anything. So remember our lovely experiment where we looked at our shooting something through a magnet, and we look at the 2 spots. So we saw this when we talked about spin. So you shoot silver atoms through a magnet, and what happens is you see these two little spots here. So you have some spin up and some spin down. That's that relation to the electron spin. So again, is it aligned with or against the magnetic field? So again, it's not top. It's just lining up. So if it's paramagnetic, it has an unpaired electron. So it gets attracted to this external magnetic field because these don't cancel out. So if you look at silver, you see that 1s orbital, or the 5s orbital has one unpaired electron, and so silver, when it goes through the magnet, you will see this. So let's talk about zinc and zinc 2+. So if it's diamagnetic, which is an atom in which all the electrons are paired, it's slightly repelled by an external magnetic field. Okay, so these are all paired, so it's net orbital 0. So let's predict the behavior of zinc 2+, the cation of zinc. So if we were to take 2 electrons from our d orbitals, remember, we wouldn't just take 2 away from here, we would have to take 1 from here, 1 from here, right? So there would be 2 unpaired electrons, which would mean that this is attracted by a magnetic field. But if zinc were to lose the 4s electrons first, then it would lose a pair, and you would have it not attracted to a magnetic field. Oops. Turns out that zinc 2+ is not attracted to a magnetic field, so it's actually losing that 4s. So that is the experimental evidence that the 4s subshell loses its electrons before the 3d one. Here's another fun fact. MRIs rely on the paramagnetic properties of gadolinium. And so it would be predicted to look like this when it actually looks like this. So they are unpaired, right? So you've got a 5d electron instead of 4f7. And so this is what allows the magnet actually, the gadolinium lines up with that magnet, and that's what causes the image to appear on film. So we have normal random atoms that are spinning around, and then the magnetic field aligns them. And then what happens is they pulse, and then it takes some time to recover. And that's what you see. The amount of time it takes to recover is how you can see the activity comparison. All right, so to sum up, here are our periodic trends. Now, I must caution you, please do not memorize this slide. First of all, y'all can use your notes when you're working on the exams and the quizzes, so I'm not really going to ask you just to spit back this information. But what I want you to be able to do is I want you to be able to explain all of these trends using the electron orbital diagrams and explaining how you would interpret experimental data that tells us how these trends, or that explains the observations of these trends, basically. Okay? So again, don't memorize, focus on the explanations. Thanks.